So during the lecture and in another video, we talked about the base rate neglect, and we used an example about a lie detection test, and given these values, which are collected from research on a specific polygraph test technique, we can assume that the polygraph test technique correctly detects deception in 85% of cases and correctly detects non-deception in 60% of the cases. And if we assume a 20% base rate, so 20% of all people who take the polygraph test will be guilty or will be deceptive, we can calculate the odds that a person is lying given that a person tests positive. And the whole goal of this is that, well, to train you to not make the same mistake as a lot of people do in making the base rate error. In making the base rate error, people tend to confuse two different probabilities. So the chance of a person being guilty given that he tests positive is swapped out for the chance that somebody will test positive given that he's guilty. So they tend to use this 85% as an estimation of the chance that somebody who tests positive will be guilty. But it's the inverse of this probability. And you should have the Sharknado hunch by now, that you know that you can't reverse the probabilities in that way. So the chance on A given B is not the same as the chance of B given A. And you should know that by now intuitively, given those examples that we use. And I also gave you an example of calculating the specific odds using a frequency tree. I explained this in the video, and we talked about it shortly during the lecture, the third lecture. In which you can take a specific population, say we have 100 people from who we enter into a polygraph test, of given the base rate and the specificity and sensitivity, we can calculate the odds of a person being guilty given that he or she tests positive. If you still think after the other video which I posted on this topic and the explanation during the lecture, still think this is counterintuitive, you're not alone. So I thought of another example of explaining what you're actually doing when you're calculating the odds using the frequency tree or using the base formula from the book. And we're going to use balls in this example, or marbles, from which we're going to draw a specific marble. So we're going to use the same hypothetical population of 100 persons, which we're going to take a polygraph test, and we're going to illustrate these odds, what we're doing with these numbers using circles. So we start with a specific population. So here we have 100 people in our population on which we're going to do a polygraph test, and we know using the base rate that 20 of these 100 people depicted by these marbles or circles will be guilty, which is the base rate. So we know intuitively that this part of all these people are in fact guilty. So we have used the base rate, which is what people often neglect to do. We also know, based on the numbers I gave you earlier, that of this population, so we have in green the people who are in fact non-guilty, and we have in red people who are in fact guilty. We know that 17 of those 20 guilty people will test positive in a lie detection test, and we know that 32 of the people who are in fact not guilty will also test positive in the lie detection test. So with the overall population, we have the part which is in fact guilty, the 20% of people who are in fact guilty, and 17 of those 20 people will test positive, but also 32 of the non-guilty people will test positive, because no test is perfect, and in this case, because of the base rate problem, you will also have a lot of false positive. And what we want to do is know the odds of, given that somebody has tested positive, what are the odds that that person is actually guilty. So given that a person is a orange dot, what is the chance that a person is a red-lined orange dot? So we can neglect all the balls who are not relevant for that equation, so all the people who are not testing positive we can discard. So that leaves us with these remaining persons who will all test positive. And what we want to know is the odds that, given that you test positive, given that we look only at the people who have tested positive, what are the odds that you're actually guilty? So you can imagine putting all those balls representing different persons who have tested positive into a great bingo box, if you will, from which we're going to draw one ball at random. And what we want to know is how big the chance is that if we draw one of these balls out of this bingo box, what are the odds that it's actually a red lined ball? Which is actually a pretty simple equation. So you want to know from all the balls which you put below in the lower part of the equation, you want to know what the chance is that you actually draw a red lined ball which you put in the upper part of the equation. At which point it becomes a simple equation. So we have 17 red line balls divided by 32 green line balls plus 17 red line balls, which makes for a percentage of 35%, which is an illustration of what you are actually doing in this frequency tree. So I've put all the different colored balls next to the boxes for which they are relevant, so you have some intuitive, perhaps a more intuitive sense of what you're actually calculating, where you're calculating the conditional probabilities using the base rate in this manner.